We are very happy to welcome Peter Gibson from York University in celebration of Carlos, speaking on solution of the scalar Riccati equation.
Okay, thank you, Brian. Okay, well, it's great to be in Rio. What can I say? I want to thank, of course, the organizers, Ricardo especially, the department at PUC for this celebration, but also for being such a great place to visit over the years. Carlos and Nicolau, of course, but also many others. Fregi, in the old days, gave me a place to stay, and it's sort of become another home for me. So it's wonderful to be here. The city is fantastic. The university is great. Of course, we are here to celebrate Carlos's 70th. So I'm going to talk about something which is in some ways very elementary. This is the prototypical nonlinear ODE, which has a very, very long history. So why this topic? Well, I thought, okay, what characterizes Carlos? Well, he has Italian roots. We're here to honor him attaining the distinguished age of 70. He's interested in many, many areas of mathematics and also interacts with many, many interesting people. And the Riccati equation has all these features. It has Italian roots, as the name Riccati tells you. It's very old. Now, I don't know how you compare problem years to people years. It's like people to dog years, But after doing a great deal of research, approximately 300 years for a problem is 70 years for a person. So this was posed in 1720 by Riccati initially. So it fits the bill. Another reason for choosing this topic is I happen to be working on it right now. So that was the other reason. Here's a rough outline. Maybe I should just say a few words. So this motivation will probably take up quite a bit of time. Has to do with Schrödinger equation on the line. So this is very, very classical. And adjacent to this problem, there are some very sort of technical and difficult problems, but I'm going to stick to something which is quite classical and relatively elementary. And then in the later part of the talk, it actually gets even simpler. Okay, so the real result here is something that's quite new. I'm still not quite sure what to make of it, so I welcome your input. But just to strategize, for those who are watching, this doesn't have the usual structure of being elementary at the beginning and getting more technical. It kind of goes in the reverse. So if you need to check email or look at your phone, the first part is when you should do that. Anyways, I'll alert you when something is about to happen. So I'm going to begin with something which is a little bit unrelated, but it explains how I got to know Carlos. And so here, isospectral manifolds. So when I was a newly minted PhD, I had been working on systems of coupled oscillators as a model for wave propagation in an elastic layered medium. And something that came out of that, of course, was Jacobi matrices, finite Jacobi matrices. And I, had been playing around with the spectrum of these things. So symmetric tridiagonal matrix with real entries. And for this to be a Jacobi matrix, you have to fix the sign of these off diagonals, either positive or negative. It doesn't really matter. But, there arose a question in my mind that, what about just all symmetric tridiagonal matrices? Can you understand the topology of the set of all such matrices of a fixed size if you fix the spectrum? That's just a question, It had come up for technical reasons. I was looking at inverse spectral problems. And I came up with what I thought was a very interesting result, which was by purely, essentially combinatorial methods, describing the topology of such objects in each dimension as a polyhedral complex. So without really going into the details, you start with, in dimension n, a permutahedron of dimension n minus 1. And you glue these together to get something which is topologically equivalent to the manifold of interest. And this polyhedral complex is interesting because you can do all sorts of computations. So for example, you can compute the Euler characteristic. Now in this example, okay, I've got a gluing rule and so on. Don't need to worry about the details. This is a two-hole torus. So already, so for 3x3 matrices, you get something kind of interesting. You calculate the Euler characteristic, so alternating sum of the counts of the faces of increasing dimension. And here you get -2, which tells you what it is. Okay, so what happens if you do that in every dimension you do the computation? Well, you get a very interesting theorem. So for this 3x3 case, you get -2. But if you calculate all of these and you write out the corresponding power series, ta-da, hyperbolic tangent. Beautiful result. Okay, so this was wonderful, and I haven't written the attribution here because I then discovered that a certain Carlos Tomei had gotten this result in 1984. I was, oh, it's famous Duke paper. I was, who is this guy? So I was devastated. The bonus was, the positive was that I think a certain Percy Deift may have noticed this preprint and said, Carlos, hey, maybe you want to talk to this guy. And I met Carlos. So, you know, it ended up being great. So here we are in Toronto in 2017. So Carlos has many academic distinctions. I won't go through them all, but one of them was he was the first Fields Research Fellow at the Fields Institute in Toronto. So they had inaugurated a new program beginning in 2017, and he was there. And it just so happened that the Coxeter lecture in that same year was given by Percy, and it was a complete coincidence, so everybody was there, and it was a bit of a reunion, and there was also a program on scattering. So Carlos has been a wonderful influence, and we've heard all these stories about him. I won't repeat them all. Of course, he's very gregarious, but I would like to add that he's not just gregarious, but very kind, and he's always been extremely positive to me and supportive in a mathematical way. And this has been very good for me. And you know, he's positive about everything, even when things go a little bit wrong. And I can give you a non-mathematical story to that effect. So you know, as a Canadian tourist, before you go to Rio for the first time, your head gets filled with all sorts of warnings about what you should not do, where you should not go, and you know, you shouldn't go into comunidade if you don't know anybody there, if you don't know what you're doing, and so on. So anyways, I was here visiting Carlos, and we went hiking in the mountains, you know, in the jungle basically, and everything went wrong. So we got lost, and we didn't know where we were. And then on top of that, I got attacked by killer bees. Now this is literally true. I got swarmed by killer bees, and on the bus trip home, I counted 24 stingers that I pulled out of my arm. So, you know, this was not going well. And you know, there was Carlos, and he was cheerful. And, you know, it became clear that he was concerned that I might be getting a little bit worried. So anyway, so we stumbled into a favela, and Carlos expressed it, you know, he said, oh, great, we've made it to a favela, I'll ask for directions. And of course he did, he went and he talked to the woman there, and I was having trouble understanding what she said. So I asked, Carlos, what did she say? And he said, well, she said, watch out for the big yellow dog. And I was like, oh, no. the day is never going to end. Anyways, we made it to the beach and we survived, and it was a fantastic adventure. But, there's Carlos worrying about my well-being and wanting to, I'm sure he didn't believe everything was rosy when we stumbled into where we did. But
Coral is a bee eater.
Okay, so anyways, I feel very lucky to have gotten to know Carlos, and this has been wonderful. Okay, so now I'm on to the first part of my talk, which is really motivation for looking at the Riccati equation. I'm going to go into some detail here about the Schrödinger equation, because I just want to illustrate how there's a special operator that comes out of this, which turns out to be useful if you want to write things down explicitly. Okay, so that's kind of my goal. So you can write down the Schrödinger equation in various forms. So this is and this is all on the line in one dimension. So this is the so-called impedance form of the Schrödinger equation. So U here is your wave function. Usually we think of sigma here as a spectral parameter. I should say my original motivation for looking at this was really acoustic imaging in layered media. So I was concerned with a particular case of interest in geophysics where you have a layered medium which is sort of varying smoothly, and then you have discontinuities, which in geology comes from things which are called nonconformities, where you've had erosion and then deposition on top of that. So it's a very natural model. And so for me, this is the Fourier dual variable to time. So this is just the Fourier transform of the wave equation in one spatial dimension, where you choose your variables to be travel time variables, and you get exactly this form. So you have this acoustic impedance, and I'm interested in the case where this has jump discontinuities in it, this zeta function here. So this is a positive function of the real variable x. Okay, so that's sort of a technical point, but it means that when you look at the Schrödinger equation in various other forms by just straightforward changes of variables, you see that you run into problems. So for example, in the classical state, so here I'm assuming there are no bound states for technical ease. So here we have the classical 1D Schrödinger equation in the time invariant form. So Q is the quantum potential here. And then of course you can write this as a first order system. Okay, so various forms, and it turns out it's very useful to switch between these. It's very annoying as an audience member in a talk if you haven't been working with this. But I just want to give some names here. So this zeta is acoustic impedance. John Sylvester calls this quantity, so the logarithmic derivative of impedance, he calls that the index of refraction. I'm not sure whether that's justified physically, but in any case, that gives a convenient name for this logarithmic derivative, which will come up all the time. It's the index of refraction. And then, of course, you have the quantum potential. Now, the issue is if zeta has a discontinuity, then you see that we have singularities that get worse here as we go down. So the index of refraction has a singularity in the form of a Dirac function. The quantum potential, you have two derivatives. You're in h minus 2. And so that's something where the existing theory breaks down completely. So I was interested in looking at this equation, doing inverse scattering in sort of the minimum regularity setting. That was the original motivation. Okay, I'm not going to go there now because that's, it's a swarm of killer bees in terms of technical difficulty. Okay, but this first order system will come up a lot here. So these are effectively all the same equation in various guises, and we need to keep in mind the spatial parameter, which is the object you want to understand, either impedance, index of refraction, or quantum potential. Now, this relationship between the index of refraction and the quantum potential is interesting. It just so happens the potential is what's called the Miura transform of the index of refraction. So, of course, this comes up in the relationship originally between KdV and modified KdV. So Robert Miura notice that this transform allows you to pass between those two nonlinear equations. So if you know solutions to one, you can get solutions to the other. Depending on which direction you're going, you may have to invert this. Okay, so in the present context, if I know if I know a solution to this, or if I have an equation of this form and I want to apply methods here, I have to be able to go backwards. So if I know Q, I want to be able to find alpha. Okay, so that's some of the motivation here. Okay, well, let's talk about forward scattering for this just briefly, and I'm going to sort of simplify things a little bit and just look at the left reflection coefficient. Really, my goal here is to get explicit formulas. Okay, so that's the objective here. Now, okay, so if we're talking about the classical form of the Schrödinger equation, you can look at a special solution F, which has this asymptotic structure. Okay, so it's this purely oscillating thing at positive infinity, and it's a mix of left and right. We call these left and right going waves, which makes sense only if you transform to the time domain where things are really moving. Okay, of course, this is not, nothing's actually moving here. But this defines a reflection coefficient, which is, you think of this as associated with what you would measure in a time experiment. This corresponds to an echo to a pulse that you would send in. Okay, in any case, that's the reflection coefficient. And you can formulate this in terms of any version of the equation, and you get the same R. It's the same thing. Okay, so for example, if we're talking about the first order system, the way I described it on the previous slide, you have A and B, so it's just a 2x2 system. A and B, and if you have an outgoing radiation condition to the right, so A you can think of as the left moving component and B as the right moving component. That's the reason for choosing the coordinates the way they are. So if you have an outgoing radiation condition, so nothing incoming from the right, then the reflection coefficient is just the ratio of this. So you see you have this vector and you project to get the reflection coefficient. So actually you could look at this projection, this is at 0, but if you look at it at x, then you get a function in x which satisfies the Riccati equation. Okay, so we can see Riccati equations coming up. In any case, forward scattering is the problem of you're given whatever physical parameter you choose, and you want to say what is the reflection coefficient explicitly in terms of those. Okay. So now things get a bit technical. Okay, so so this is the time to answer email. So here we have the first order system where we have this coefficient matrix which happens to be of this form. So this sigma you can think of as the parameter, this is the frequency parameter, so that's constant. And then we have alpha, I'm writing this in terms of the index of refraction alpha. So alpha is a function of x. And we have this system of this form. Okay, so you can think, it's better if you want to write down the general solution to think of the corresponding matrix equation where G is a 2x2 matrix here. So it's the same equation, but I'm just replacing this with a 2x2 matrix. And I'm fixing an initial condition of being the identity for all values of the frequency parameter. Okay, or you can write in terms of the inverse matrix to GH, and you get a corresponding equation here. So these you can go back and forth. That's very straightforward. It turns out for technical reasons to be nicer to work with H, where you have multiplication on the right here. And just notice that this happens to belong to the Lie algebra SU11. Okay, and so the solutions, if you can write them down, are going to be in the corresponding group. And this is something which is very well understood in mathematical physics, except that they don't have explicit formulas for these things. They just say, well, you take an ordered exponential, but there's something to be done there. Okay, so if we can find an explicit formula for H in this 2x2 matrix equation, then we get one for R, which is what we wanted. Okay, so let's start with this little 2x2 matrix equation, and we'd like to solve this. And it turns out that there's a special equation which you wouldn't guess, which turns out to be of importance here. And the interesting equation involves just a little notion of duality here. So if I have a function f, so f is just a generic function here, of a real variable and a complex variable, I can define a kind of dual function which is just given by this formula. Okay, so I take the complex conjugate of, now I'm complexifying here my frequency variable. Of course, this is done all the time with the m function in scattering on the line, which I don't like the m function, so this is one of the reasons for taking this other approach. So anyways, you have this kind of duality, and you can see it's, if you do this twice, you get back the same thing, right? So it's involutive. Anyways, once you have this duality, you can think of this little equation here. Partial derivative of f of x is index of refraction times dual. Cute little equation. And you set an initial condition here, constantly 1 independent of sigma. Okay. This has a solution that you can write down. Okay, so the solution looks like this. Okay, it takes a minute to digest this formula, but okay, so here I have a series which depends on the index of refraction. It's a function of two variables here. Spatial real variable and this complexified frequency here. But what you have is an integral, at the jth term here, you have an integral over a j simplex of this phase function times tensor product of the index of refraction at the various variables. So it's actually very simple, and this phase function is just the alternating sign. This kappa here is just the alternating sign of these variables. So that's why I call this harmonic, because of this phase term, and it's sort of exponential. In fact, if sigma is 0, it really is an exponential function. So that's a natural thing. Okay, so once you have the formula, you can check that it satisfies this equation. It falls right out. There's nothing to prove there. Okay, it just follows from the formula. You can see that it works. But then the fact that it satisfies this equation means we can use this formula to actually go back and solve the original 2x2 matrix equation, which is this. So here we have our 2x2 matrix equation. I've put things on the other side here. And okay, I need to invoke this special matrix here. 1, 1, minus 1, 1. Okay, so that's not too alarming. Okay, but if you take the exponential times this matrix times h, that's what it is in terms of this harmonic exponential operator, and it's dual. Okay, so very nice formula. To prove this, it follows exactly from the fact that this operator E alpha satisfies that little harmonic exponential equation that I formulated. Okay, so once you have H, you can formulate G, and you get a general solution to the Schrödinger system here. Okay, so of course this is an operator. Alpha is a function. E alpha is a new function of two variables. So if you think of alpha going to E alpha, that's the operator. And if you think of this as being an exponential type operator, then you have corresponding hyperbolic cosine, sine, tangents, etc. Okay. Now here's the theorem. The formula for the reflection coefficient in terms of this operator is hyperbolic tangent. There it is again. Curious. Hyperbolic tangent in a completely different, in an operator theoretic sense appears here. Okay, so the proof is completely straightforward. Once you have the solution to the 2x2 system, we have a formula for A, and you can just write down what the reflection coefficient is based on this projection here. Okay, so again, the goal for explicit formulas is not just to have explicit formulas. Ultimately, you want to do acoustic imaging, and let's say in my case. And when you have an explicit formula for the forward map, it turns out you can get an explicit formula for the inverse scattering transform. And that is in such a form that you can code it up easily. The formula tells you how you should encode it in terms of a computational algorithm, and it works. Okay, so I'm not going to talk about that, but this is actually a crucial step, this explicit formula, for the ultimate goal, which is the inverse scattering. Okay. Okay, so there is good reason to want such a formula, and here it is, and it turns out to be surprisingly nice. Okay, so we have this nonlinear relationship between alpha, the index of refraction, and the data, but it's a nice nonlinearity. It's a kind of, in spirit, it's a hyperbolic tangent, you know.
So, I'm sorry to interrupt you, but this is so miraculous, right? So what you're saying is that you have a formula given by a series,
Yeah.
which somehow would compete in terms of series with, say, iterating the second order linear system, PUC-Rio, right? But your formula is more natural, in the sense
Yeah.
that it's more physical, right?
Yeah, I mean, ultimately that Picard iteration I'm going to talk about in a second. Exactly that. That's where it comes from. Yeah, David.
In your initial data, there were discontinuities, right? So that class formula reflects this E.
Okay, so that's a very good question. I was originally concerned with discontinuities, and what I've swept under the rug is here I really want alpha to be locally L1. Okay, so here there are no discontinuities in the zeta. Excellent question. You can handle those, but that's another story. You have to look at almost periodic structure, and it can be done, and it's very interesting, but it's, yeah, Andre.
Yeah, interesting. So also, can I read this as that you get total reflection, meaning 1 as sigma increases? Is that what it's saying?
No.
Total reflection on.
No, so this is a formal hyperbolic tangent. It's not the hyperbolic tangent function. It's what you get if you take this formula here, this formula, this operator, and you add it with, okay, so here we have alpha and minus alpha. You combine it in the way that we build up hyperbolic tangent formally from the exponential. So it's not, it doesn't have those characters. In fact, this reflection coefficient, if you complexify sigma, it's an entire function with respect to sigma, provided, as David pointed out, alpha is locally L1. This is entire, and it's more than that, it's zero free in the upper half plane. Okay, so it has beautiful structure. But I'm not going to talk about that, right? So it doesn't behave like the scalar tangent function in quite the same way. Okay. 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 You do get a tangent if you set sigma to 0. Okay, but then going hyperbolic tangent, right? So it's 0 free. Okay, but. Okay, so let me just continue here. So this applies to the classical formulation of the Schrödinger operator, but because my formula is in terms of alpha, index of reflection, we need to invert the Miura transform, right? This is the relation, so we need to invert this. So that's kind of the motivation for the talk. I was always frustrated by this. And of course, in talking to Carlos, he's been here before me too. He's dealt with the Miura transform, but on the circle, so it's different. So phew, you know, he hasn't scooped me on this one, I hope, with Nicolau, of course. Okay, well, so you can write down an explicit formula for the Schrödinger equation, which is, okay, so there's much more in this paper. But I just wanted to write down formally, this looks somewhat horrible, but here, this is the impedance form, this U, you can write down in terms of this harmonic exponential operator here. Okay, so now back to what Carlos was talking about, this Picard iteration type thing. Exactly, so you have this equation, and then in physics, okay, so what do? will you evaluate an ordered exponential, which is this funny symbol. It's kind of like a product, an integral of products of matrices, so you have to worry about the order. And what do? You have this coefficient m. You take I plus m evaluated at a grid point, and this gives you a matrix. You multiply this over the grid points, but in the right order. Take the limit as the grid goes to grid width goes to 0, and then you get this. Okay, so there's a whole theory behind this, but the problem is if you want to know the individual entries of this thing, you need something more. Okay, so I'm going to explain where this funny equation, this harmonic exponential equation, comes from. So you look at this, and you look at these individual factors. Each of these matrices, well, you have 1 plus I times delta sigma, etc. Now, something to notice, because we're taking an n going to infinity limit, or grid width going to 0, 1 plus I delta sigma is approximately the exponential here. And 1 minus I is approximately this exponential. And this approximation is fine because we're taking n to infinity, so this is not an issue. And, you know, if you just stare at this and play around, and let's call this z, okay? So this is something on the circle, but let's call it z and sort of complexify. So set z to be that. And let's give this a name. This is an r. Then we get a matrix like this. And now I want to think of z here really as a complex variable. So I'm going off the circle and I'm complexifying, which we do if we allow sigma to be complex. So, okay, so this now I want to think of a matrix with z, the complex variable, and then these are constants. It's the same constant and 1 here. These are real, actually. Okay, this is just for technical reasons. I have this diagonal thing, and you can write this matrix as this thing. So the matrix that comes up in our computation is diagonally similar to this. Okay, so what you end up with is that approximately the h you're looking for, if you multiply by this simple 1, 1, minus 1, 1 matrix and this phase term, you get a product of these matrices. Okay, you pre-multiply by the constant matrix, and then you have these which depend on z. So these products of n 2 by 2 matrices with these, this is a classical object. Okay, so this is a classical object. This thing is a classic formula for orthogonal polynomials on the unit circle. So if you take initial products of this big product, you get something which is very obviously a polynomial of degree j, or at most j, in each of the entries. Okay, so I'm not going to, but there's a massive theory of these things. And so this should be useful. It's an interesting connection. All right, so this is an old theory. It's well developed. In particular, there's this duality relation. We have two sequences of orthogonal polynomials on the unit circle which pop out of this, psi and phi. If we just look at the phi's here, we have the relationship between the dual, which is the star, is this. Okay, if you take the n going to infinity limit of this, you get the duality that I started with, the continuous duality. And if you take the classical 3-term recurrence for these polynomials, which I haven't written, you get this equation. So this is the renormalized continuum limit of the 3-term recurrence. So this is the continuous 3-term recurrence. Beautiful. Okay, so that's really nice. And you get this special function, which allows you to solve the system. Okay, so that's the result. Okay, so this is sort of the situation, and I was discussing this with someone at a workshop a couple of years ago, and he said, yeah, well, okay, you have a very special example of a SU11 coefficient matrix, but can you do the general SU11? I'm like, well, so he wants the frequency now to depend on X, which doesn't make physical sense from the perspective of the problem I was thinking about. So I told him, no, that doesn't make any sense, really. Right? So, but he's like, well, no, because I want more. So anyway, I forgot about it for a while, and then I came back to it, and I realized, oh, there's a simple way you can do actually all of SU11. You know, and then he says, well, what about SU2? I'm like, oh, come on, give me a break. It's completely different, right? So how am I supposed to do that? And of course, you can keep going with SL2C, and then if you really want to go crazy, what about an arbitrary thing? I mean, can you do the same thing? Okay, so I think the expectation here is that, okay, so given where we got our very special solution, if you want to go this way, it's going to get horribly messy. That's the intuition that I had anyway. And of course, we want to invert the Miura transform ultimately. So that's also playing into this. Okay, so here we have this hierarchy of problems, and that's sort of the end of my introduction. Okay. Okay, great. So I have a little bit of time left to actually tell you the real story. Okay. Okay, so Riccati equation, I'm talking about the scalar Riccati equation. There's a classic handbook on solutions to differential equations by Erich Kamke. This was originally published in 1944, and is all the solution tricks sort of at the undergraduate ODE level for various kinds of ODEs. So it's a great book. And of course, it talks about the theory of the Riccati equation. And if you jump to more recent handbooks, you see that this Riccati theory has frozen. Not surprising, because it's an old problem. It's 300 years old, and many luminaries worked on it. Euler has papers on the Riccati equation. Abel has papers on the Riccati equation. Liouville gave a beautiful characterization of when you can solve the Riccati equation explicitly by quadrature for a certain class. Okay, and Watson has worked on this as well. Okay, so anyways, it's not surprising that out of that history there has distilled an essential theory. Now, the Riccati equation has many current connections, flows on Grassmannians, Cartan-Siegel domains. Here, this is a really wonderful book for contemporary connections of this Riccati equation. So it's not a dead thing, and it's connected to some very rich mathematical structure. But I'm just going to talk about completely elementary things here, which is that if you look at the general theory a la Kamke, what you have. So here's the equation, and I want to take my coefficients here to be arbitrary locally L1 functions. Okay. So there are some general theoretical results, and then there's a second part to the theory. So the first part says, well, if you know a particular solution to this Riccati equation, you can find the general solution by some change of variables. Fine. If you can transform this nonlinear equation into a homogeneous linear second order equation. Very important, right? And it's interesting, Kamke actually says, which may be easier to solve. Okay, and then if you go to these more recent handbooks, they all say it may be easier to solve this, but they never give any examples. And the reason there's no examples is because really it's equivalent and it's not easier to solve. That's a lie. Okay, but anyway, this is very important. If you have any four distinct solution and you look at the cross ratio, that's constant. Okay, so this is where I have to tell Nicolau, cross ratio, geometry. This is where things are happening. Okay, and you can transform an equation like this by suitable change of variables to a sort of canonical form in which this g is 0, and effectively the canonical form is very close to the Miura equation. That's a bad sign, because if we want to invert the Miura transform, we have to kill the whole Riccati problem. So that means it's not going to be so easy, and there's a reason why there isn't a formula for inverting the Miura transform, because it's connected to this. Okay, there are many sporadic examples where you can get a solution if you choose things nicely, if these are constant, for example, or if it's, f is 0, then it's linear, et cetera, et cetera. And some of these are kind of wild to just show how crazy this can get. Here's a paper from 1991 in which yet another case of integrability is given. So here's the Riccati equation. GRE is the general Riccati equation. That's the equation we're talking about. So it's this equation. And he says, if f plus g plus h is equal to this horrible mess, and alpha, beta are chosen suitably such that, then you can make this change of variables with these horrendous formulas, et cetera, et cetera, et cetera. So, okay, you can imagine if somebody has a computer algebra package, whatever, Mathematica, you could go wild and find something even worse. Okay, but it looks like that's it. You have these sporadic things which are not nice, and then you have some general theory, but you don't have a nice solution.
That's the beginning of the paper. That's
No, this is sort of in medias res, just the theorem here. So this is the paper, and then, okay.
It's
So
a two-page paper.
it's short, yeah.
so there is not much of an explanation of where that came from.
No, it comes out of the clear blue sky. So, okay, so that's the annoying thing. Okay, so let me talk about, this is fresh off the press, so just posted to the archive. Okay, so here's just a very simple, trivial observation, really. If you're integrating over a simplex, and you have a symmetric function, that's the same as integrating over the cube and dividing by j factorial. Why? Because these simplices, if you permute the order of the variables, they're all congruent, and there are precisely j factorial permutations. Okay, so that's just the integral over the cube is the same as that. Okay, so that's easy, but it's useful. Okay, so of course, you know, one of the workhorses in introduction to ODEs is the exponential primitive operator. So here I use this p for primitive because I want to write this operator without an x in it. So this p of f is just the primitive of f normalized so that 0 is 0. Okay, so this is just an antiderivative here, but I'll use this notation. So p is for primitive, so antiderivative. Okay. So this primitive operator, of course, inverts logarithmic derivative. So you solve the most basic ODE this way. But of course, because this is an exponential, I just write this out using the scalar exponential formula. And I use my previous trick to write this out as an integrals over simplices instead of cubes. Okay? So if you look at the primitive of psi to the jth power, that's actually an integral over a cube, and we're dividing by j factorial, so I'll rewrite it as an integral over a simplex. Okay, and we just have this tensor product of psi with itself j times in each term. Okay, so, okay. Now, here's an idea which somebody could have easily just thought of. Okay, so instead of one function, interleave two. Okay, so now we have two functions, psi, eta. We take the same formula, but we interleave them, psi, eta, j times in each term. We get something which has very similar status as an explicit formula, as in terms of convergence, in terms of ease of analysis. It's almost the same, has the same status, but it's bivariate. You have two functions that go in. So this is the exponential primitive operator. This is the corresponding bivariate exponential primitive operator, right? So actually, when you have something of a single variable and you get a multivariable analog, that's called blossoming in computer-aided geometric design. It's a known thing in algebraic geometry. Okay, so anyway, it's a very simple example, a perfectly natural thing. This is a beautiful formula.
So when j is odd, you have one more side.
Exactly. This is exactly, the parity of j is exactly the issue. Okay? So when you have an even thing, the last term is balanced. The last term is eta. When you have an odd number, the last term is psi. And when you differentiate with respect to x, you get the thing that's the last term. Okay, so let me just say, that was written for x positive. If x is negative, you have the same formula. You just have to notice you have a -1 to the j that occurs if x is negative. And then you have to write the variables in this order. So xj is always closest, sj is always closest to x. S1 is always closest to 0. Okay, so this extends this formula to all of R. It's the same formula. And then, as Nicolau was pointing out, you might want to pick off the even and odd terms. So let's pick off the even terms and call this CE for cosine of some kind and S for sine of some kind. Okay, now we've picked off the two. These are always odd numbers of terms. These are always even numbers of terms. Okay, it's very easy once you have that to prove this lemma that if you differentiate the collection of terms with even, you get g, the second function times this. You differentiate the odd terms, you get f times that. Now this is magic. Okay, the fact that it has this property. Okay, so watch what happens. you can, if I have three functions, f, g, and h, I can make a matrix out of these c's and s's. Okay, so now I have to build things up a little bit. This capital F is built from these three things. It's minus e to the primitive of g to the f. Capital H is e to the minus primitive of g to the, times h. So very simple connection between these and these variables. And then you write down this 2 by 2 matrix, and that does everything for you. Okay, so for example, if you take an arbitrary coefficient in SL2C, and this is your coefficient, so SL2C just says that this should be trace 0. Okay, which it is. Then your solution to this matrix equation is this matrix. Okay? It's m equal to this. That's your solution. That's the general solution. Okay, so it's not, it's actually easier, it's simpler than in the SU11 case. And in fact, you can push this a little farther, because if you have a 2 by 2 matrix, you can shift by the trace, and you can handle an arbitrary coefficient matrix. Okay, well now we can say something. If we have an arbitrary second order linear equation, of course you can write that as a first order system. It's got some coefficient, so you can solve it explicitly. You write down the solution and look what it is. Okay, so here's an arbitrary linear second order equation. This should be, you know, a second year undergraduate class. There's the solution. Y of 0 times C, Y prime of 0 times S. Where these f and g are related to the coefficients alpha and beta. These are arbitrarily locally L1 functions by these little formulas involving beta times the exponential primitive and just the exponential primitive here. Okay, so that's just, you write down the solution to an arbitrary second order linear equation. Okay, so if you want to do the arbitrary Riccati equation, you have to do a little bit of work. Okay, if I have a matrix here, it corresponds to this linear fractional transform. Everybody knows this. So a 2 by 2 matrix gives you a linear fractional transform. Okay, and this is an automorphism of the Riemann sphere, right? So this is represented by P, strictly speaking, SL2C. But this is well known. Okay, so the fact that this is the automorphism group of the Riemann sphere is something I would love to talk about if I had more time. But I'm running short. Okay, so if you have a matrix, you have a linear fractional transformation. If you have a matrix valued function on the real line, you have a linear fractional transformation valued function, which takes values in automorphisms of the Riemann sphere. Okay, so for present purposes, the Riemann sphere takes the metric you get from stereographic projection. I mean, this is perfectly reasonable. Now I have to take one minute to talk about a standard solution to the original equation is one which satisfies the equation almost everywhere, because we're just assuming that these are locally L1. But where the function y is locally absolutely continuous. That's it. That's a standard solution. Now, of course, you can have infinities, but on the Riemann sphere, you're in a nice homogeneous space. Those infinities are the same as any other point. It's quite natural to define a projective solution to be almost the same thing. This has to hold almost everywhere, but the stereographic image should be absolutely locally continuous. Okay, effectively the same thing, it's just that it means you can go through infinity and there's no problem. Okay, so we have projective solution is that. It's a slight weakening of the standard solution. And of course we say a transformation is said to generate solutions. So now I'm taking this as a path in the automorphism group of the Riemann sphere, which goes through the identity at 0. It's said to generate solutions to the Riccati equation. If I define y to just be, okay, take a point x, I evaluate my matrix at x, I take the corresponding transform, I evaluate it on the initial data. If that satisfies this equation with initial data y0, then I say that this transform, phi m, so this is a path in automorphism group of the Riemann sphere, generates solutions. Okay, so just standard solution, projective solution, and then we have this thing which we say generates solutions because you evaluate it at x and at an initial value and you get the actual solution to that. Okay, so let me just say there are issues with dividing by where you get infinities. You may want to know where you get infinities, and you can completely characterize that by saying, well, okay, this minus d over c here is the set of points where you have to worry, where you get a 0 in the lower part of the linear fractional transformation. So that's when you have this value. So this set of points I call my singular curve, and it has measure 0 in the complex plane. Okay, so that's not so important, but here's the theorem. Okay, so let me end by saying, if you take an arbitrary Riccati equation, then for every initial value off this measure 0 singular curve, the solution you get by exactly the same construction. So we build the same matrix as in the 2x2 solution. We write down the corresponding curve in the automorphism group of the Riemann sphere. You get that. That is a global solution in the standard sense. But you can even go further. You can say, well, what happens on the singular curve? Okay, provided you have some weak properties that f, the coefficient of y squared, satisfies, the nonlinearity, as long as it's not 0 too many places, it's a global projective solution. So you always have a global projective solution, no matter what, and it's given by this formula, and actually you can write the formula out. It just looks like this. Okay, very nice. Formula to the full Riccati equation. And now you can play. You can say, well, take your favorite equation. Let's go back to, well, here's a beautiful case that Abel worked out, where he made this weird hypothesis that f, g, and h are related by this. And he found a formula which is just tangent. Okay. Now, how Abel did that, God only knows, right? But we can just write it down. Okay. Now, let's go back to Schrödinger. Remember, I had that ugly solution to the Schrödinger equation? Now you can just write it down, and you can just write it down in terms of Q directly. Boom. Explicit solution to the Schrödinger equation. The funny thing is, I did all this because I wanted to invert the Miura map. But if you can do that in terms of Q, you don't need to invert the Miura map. So I didn't need to do it because I did it. Okay, so that's weird. Okay, so if we look at okay, so this is the Riccati equation corresponding to the Miura map. This is the general solution to the inverting the Miura map. Okay, so this is very interesting because this is globally a projective solution. It guarantees to exist for any initial condition. So you can, so Carlos and Nicolau studied the Miura map on the circle, where you have this funny situation of you only get finitely many solutions.
It's a global fold, right?
So you get two.
At most.
At most two solutions. Here you have the full line of solutions, guaranteed, as long as you're allowing to permit. Of course, you can go through infinity, right? I mean, it appears to be a singularity if you're working with some physical quantity. Where it goes, but on the Riemann sphere, that's this homogeneous space. It's not really special. You can even set infinity as an initial condition if you like, and everything's well defined. Okay, so Percy mentioned the Airy function as an integral kernel. You have a pair of Airy functions. You can apply this to the Airy equation, and you get new formulas for the Airy function. These two functions satisfy the Airy equation. It's interesting, you look at this integral, you're integrating every second variable here at these. New formula for the Airy equation. And you can write down the classical Airy functions in terms of these. Okay. But the key to everything is this very simple operator. And with that, let me just say, happy birthday, Carlos.
So, any questions?
One issue is that in the related problem of recovering the potential from the reflection coefficient, there's an explicit formula and the determinantal formula due to Dyson. And I wonder if that formula has any relationship to the formula you represent.
That's an excellent question, because there's also an issue, if you want to do inverse scattering, then these singularities do become an issue, because you want, okay, so the explicit inverse scattering formula, so I know Dyson's formula, yes, I'm not sure, okay, so I would have to think about that to give you a short answer. But in other explicit inverse scattering formulas, you need some regularity. So for example, you want if you're looking in terms of the index of refraction, that should be locally L2 for the formula to work. And then this fact that you're allowing projective solutions is not okay, because you don't necessarily have the sufficient regularity. Okay, so you have these singularities in Q, which may also be singularities in alpha. Okay, so that could be an issue. But anyways, Percy, to answer your question, I'm not sure. I have to think carefully, because I think so. The determinantal formula, yeah. Of course, it ought to be right, but.
So can you extract any asymptotic information, for example, about the Airy function?
Oh, okay. So I was afraid somebody was going to ask me. Basically, I know nothing about Airy functions except that I can write down a new formula for them. That's a great question, and these are very well-behaved integrals. So it's worth exploring, and I don't have an answer, but I just met this past year somebody who's a pro in representation of Airy functions and things like that. So I'm going to ask him for that. But yeah, thanks for the question.
So I'm not gonna ask you any questions, rather try to give some input. And what I'm gonna say is just in the case of the smooth setting, so I'm really not used to work with L1 functions. So in your first slides, where you basically put the homogeneous 2 times 2 linear system with the matrix n. So the way that I think about that geometrically is that what you're really defining is a connection, a principal bundle whose group is the group in question. And solving the question is basically computing the lift horizontal curves for that connection.
Exactly.
And the formula that you use, at least it's familiar to me under the names of chain iterated integrals. And maybe, I mean, if you look into that, you could get some feedback and some ideas, because I mean, block techniques go back to the 70s.
Yes.
You can use it for any Lie algebra, so you basically will be solving explicitly the corresponding homogeneous.
Yeah. So I have looked at that. So it has many names. Like, so you have, it's sometimes called ordered exponential. Sometimes it's called product integral, and so on. And so yes, it's very. It even goes back to the late 19th century. This ideas, but as far as I can tell from looking at that theory, is it gives you a way of solving the matrix equation, right? But if you want a formula for the individual entry in your solution, it's not at all clear how that comes out of the method. So whereas here, because we have this individual function, it's really this. You're just manipulating this scalar function. This gives you formulas for the individual entries, and so it's very old. Yeah.
So let's kind of stick to the question back here. So in principle, you could have a catalog. I mean, you did it for the Airy function. In principle, you could write any special function in terms of that class.
Well, any special function that corresponds to a second order equation. Okay. Yeah. Because of course, you have higher order. Potentially.
Let's think about the second order. So you should have a catalog between that type of that solutions you define, and then this, let's say, second order special functions. And the natural question is then if this catalog has any systematic dictionary could be written. So,
That's a very nice comment, and yeah, this literally went onto the archive this week, and I haven't even looked at these things. I mean, I think there's a playground now to start trying to figure out really systematically what is this telling us. But yeah, so the area function was something I tried, and it comes out. It has a very nice formula in this sense. But yeah, I like that comment. Thanks. Yeah.
More comments, please, or questions? Thank you for your hand.